using a particle picture.
Okay. So I hope everyone can see the video. If you can, just say yes. Yes.
Yes, sir.
Yes, sir.
So I want to play this again because it's very important that we understand. Although Feynman had said that nobody understands quantum mechanics, but we'll try to get used to this quantum mechanics. And in order to get started with quantum mechanics, it's very important that you uh, know about this double slit experiment and a little bit of history. And history is shown here in this particular slide. Newton believed that light is made of particles. There are people like Huygens who say no, light uh, light shows what is known as interference. Hence, light is nothing but wave. And then Maxwell came up with the electromagnetic theory of waves. Later in Einstein's explanation of photoelectric effect, he had to assume that the light is made of photons, and these are like particles with a with a fixed energy. If you give me the frequency, the energy is h times that frequency. And in the experiments of Compton, uh, light also behaves like a beam of particles. So you have all these things. Light in some experiment is like a wave, and in some experiments like a particle. This is with light. What happens when you do the experiment with something which you know as particles, for example, electrons, and that is what is being done in double slit experiments with electrons. That is discussed in the last class. So I'm going to play the video for maybe 10 more minutes, and from there we'll again start discussing.
But then, of course, it is also known that light exhibits the phenomenon of interference, and therefore it has a wave nature, and therefore scientists were very puzzled. So they were puzzled because, you see, it appeared to them, this is only a joke, it appeared to them that on Mondays, Wednesdays and Fridays, light seemed to behave like a particle, while on Tuesdays, Thursdays and Saturdays, it seemed to behave like a wave. And naturally, that is the way it is. You have the question, what about on Sundays? Well, the scientists of those days, and this, as I said, is only a joke, scientists of those days would go to their place of worship and perhaps pray to God as to a clarification whether this is a particle or a wave. But now it is clear to us, actually, it is quite well established that light has a dual nature. Not only light, it appears as if everything in this universe has a dual nature. That even electrons, neutrons, protons, helium atoms, C60, which is a rather big molecule, this also has been demonstrated to have a wave nature. So people have been trying to show this wave nature experimentally. For different particles, they have succeeded for electrons, neutrons, protons, even for bigger systems like C60. But of course, you see, we don't have experimental evidence for much bigger systems. If somebody says that I have a wave nature, a big particle, you can say, okay, I would probably be expected to have a wave nature. There is absolutely no experimental evidence. So we would like to extrapolate and say that even bigger objects have a wave nature. So this is a C60 molecule, a nice football-shaped object, and I want to show you experimental data taken from the group of Anton Zeilinger. His name you will see in a second. So you can see the interference pattern that he found. Okay.
So this group is from Austria, Vienna, experimental physics group. So last class we showed that they interfere. Electrons they interfere. For example, one electron interferes with itself. Okay, so if I have two holes and if I shot an electron gun and one electron comes like this, and when it sees two holes, it behaves like wave and it passes through maybe one of the holes, because if you see that can detect whether it is going through hole 1 or hole 2, but on the screen you get interference pattern if you perform the experiment several times, several thousand times. So the whole thing is that electron which is in, I assume to begin with a particle, is also behaving like a wave. That is why it is called wave-particle duality. And if it happens with electron, whether it happens with a bigger object, bigger than electron, and that is the question. It happens with something like light, which you know, but now what happens with something which has which is a particle to us, like everyday life, which I will assume is a particle. If you give me a molecule, I will not call it a wave, isn't it? I will call it something which is a lumpiness, which has some size and like a particle. So electron, better to go beyond electron, bigger than electron. And one example is the C60, which is a big molecule. So the experimentalists showed that even a big molecule like C60 also shows this interference pattern. So it also has this wave-particle duality. So I'm going to play the video again.
This pattern, which is just an interference pattern. And this is obtained using a beam of C60 molecules. He made a beam of monoenergetic C60 molecules, passed them through those slits, and then observed this experiment, this interference pattern, showing that even a C60 molecule has a wave associated with it. Okay, these are pictures taken from his website. You should have a look at his website, whose address is given. Okay. Now, though, a few words about these two pictures. Actually, this is again another joke. These two pictures. Suppose you are playing football and imagine that the ball has a wave nature. What will happen? Right? I mean, the ball has a wave nature, and let us imagine the wavelength is rather large. Suppose that's not the actual way it is. Then suppose you say I am standing here, I am the goalie, and one of you is going to stand there, and it is a kick penalty. So therefore, you are going to shoot the ball. Suppose you shoot it directly at me. In our classical world, what will happen is that if you shoot it directly at me, and if I don't move, I mean, obviously it will not take out, because the ball will hit me and it will go somewhere else. But if the football had a wave nature, what is going to happen is that the wave associated with the football can go through this side of me or through the other side of me, and right exactly at my back, what will happen? It will be constructive interference. Exactly at my back. So therefore, even though I am standing obstructing it, it can directly go and can be a goal. Right? Of course, this will not happen if you do not have a wave nature associated.
So this is fantastic. So you can think of playing football with a football which has wave nature. Yeah. In principle, everything has a wave nature, but a football which has appreciable wave nature, then if you play football with that kind of football, this kind of strange thing can happen. So the idea is that it goes like this, and the goalie is standing like this, and it can actually bypass the goalie. It can go from the any of the side of the goalie. And then this football will meet in a sense, they will interfere at the back. And then that will be a goal, you understand? So it's like that if you kick the ball, it goes like this, sees the goalie, and as if the ball is divided into two, and then bypassing the goalie, and then again meeting with each other at the back. So this is an example of like constructive interference, and that is obviously wave phenomena, and that can happen with an electron as well as with a big molecule like C60. So let me play the video again.
Which we don't have in our real world. I mean, the wavelength associated with the football in our real world, we would expect is very small, and therefore you don't see any interference effects. Okay, well, as I said, people have been doing experiments. They have been able to demonstrate wave nature for bigger and bigger systems. What I have here is a report that is out only 2 or 3 months ago. I suggest that people have a look at this paper published in Nature Nanotechnology. The reference is here. The experiment is done with thiocyanins. So you are going to see another video now with 2 of them. So this is the molecule thiocyanin. You can see it. And these are the single thiocyanin molecules arriving at the detector screen, the spots, just like the electron experiment. These bright spots that you see are single thiocyanin molecules arriving after having passed through 2 slits. And you can see the interference pattern that has resulted, demonstrating that these also have a wave nature. Okay. So the interference patterns are very clearly visible. Again, I mean, one more video from the same set of people. There's a much shorter one which shows the pattern very, very clearly. Well, this actually demonstrates that microscopic things have a dual nature. They can behave like a particle, they can also behave like a wave, and we human beings actually have no direct experience with such things. You see, in our world, it seems that you see if I have a particle, it behaves like a particle, it doesn't behave like a wave, and if I had waves like waves on the surface of water, then that is a wave, it is not a particle. For example, there is no bumpiness, there is no lumpiness associated with the waves on the surface of water. So we have, unfortunately, no direct experience of things which have this dual nature, and therefore we find it very difficult to comprehend how can the same object behave like a wave as well as a particle. So to help you in that direction, I have taken a picture from the web. This has nothing to do with the with the wave particle duality. It's just a picture that has a dual nature. So if you look at this picture and if I ask you, whom do you see in this picture?
Okay, now can you see the picture, all of you?
Yes, sir.
Yes, sir.
Can you see the picture? Yes, yes. It may not be very clear, but you can still see the picture. And what do you see in this picture? For example,
An old woman.
someone tell me. Sachin there, tell me, what do you see? Old and
I
young.
see a young girl, then an old woman.
A guard. Somebody said a guard. Yeah. People who are very romantic, they would see, don't mind, but maybe a young girl. And
then old woman.
people like me will see both, I think. So essentially, you can see there are 2 pictures. So for example, young girl, yeah. Akila Mohan, yeah. Okay. An old and young woman, okay. So tell me, how many of you see only one? Like either a young girl or a not so young girl. So actually, if you look very carefully, you see there are 2 pictures. One is this young girl. Can you see the cursor? I am not sure. Can you see? Can you see the cursor if I take the cursor?
Yes, sir.
Yes.
Yes, sir.
So for example, if I say this is the nose of a girl and this is the ear, you can see this is a young girl, isn't it? And but if I say this is the nose and this is an eye, then you can see an old lady. So this is a picture which has two pictures hidden in that picture. So it has nothing to do with wave particle duality, but just to demonstrate that the notion of duality here. So everything in this universe has this wave particle duality. Anything, even I also have some kind of wave nature. You also have some kind of wave nature. Okay. But when you go to subatomic world, this wave nature is cannot be neglected. And how do you measure a wave nature? Can you tell me? Like how to quantify a wave? How do you quantify a wave? Can anyone answer me? How do you quantify a wave?
By its frequency or wavelength, by measuring its frequency or wavelength.
Yeah, so basically you have a frequency or a wavelength. Okay, frequency or wavelength, you have a relation for that. So for example, say let us speak to wavelength. So if I tell you the wavelength, I know, okay. So every wave would have a wavelength and that wavelength will define that wave, isn't it? Okay. Are you, everyone is fine with it? Now what
Yes.
what I'm going to do here, that there is something called a hypothesis, and which is extremely important, without which you cannot build the subject of quantum mechanics. And this was introduced by a person called de-Broglie. How many of you know de-Broglie? Have you heard of de-Broglie? How many of you? Yes. So can you tell me, he was from which country? Any idea? Any idea? He was from France, yes. So he was from France, and what he is famous for? Tell me. Matter waves, this hypothesis. So it seems that many of you actually know about de-Broglie. Yeah, actually, so far we have discussed everything very qualitatively. If you go through the notes of Professor Rahul Maitra, you will see that little bit of quantification of this double slit experiment, isn't it, Rahul? You have something.
Yeah, to some extent.
Yeah.
Yeah, to some extent. Yeah.
So maybe I suggest you all to go through that part. We're not going to discuss it here, but we can discuss it in the next class, or maybe we can have it when you take quizzes. Okay, so it is important that you please go through. It's not very lengthy thing, a very small thing there, but you should go through. So what I'm going to do here now, I'm going to introduce de-Broglie's hypothesis. Actually, de-Broglie got Nobel Prize in Physics in 1929, and for this. But it was a part of his thesis, and so far I know that people were not very happy with this hypothesis, and his thesis was not easily actually approved. And Einstein, it was Einstein who said, okay, no, this hypothesis is not, it is actually quite useful. It will be quite useful and has some substance. So what happened that because of Einstein, de-Broglie got his PhD. Without the help of Einstein, he would have not got the PhD. Rahul, you know this, no? I think it is Einstein. Rahul, are you there?
Yeah, can you hear me?
Yeah. So I'm saying that either Einstein, who was in the committee or something like that, who said, okay, no, I should not throw away his thesis.
Yes, yes,
This
yes.
hypothesis
I think so. And he's the only
makes
person,
substance.
and he's the only person who got Nobel Prize based on his PhD work.
Good. Yes. So he did this work in his PhD and eventually he got Nobel Prize in physics for this work. So now let us discuss this de-Broglie's hypothesis and how many of you know about it. It seems that many of you know about it, isn't it? It seems that many of you know about it. Anyone is there who has not heard about it? Anyone? If you have not heard about it, tell me. Is there anyone with biology background, something like that, who did not have it? During his BSc or in his first year of BS. Kapil, I don't need your video. Yes. Tell me anyone who has not heard of. Okay, I got one person who has not. Okay. So let us discuss this. And before we discuss, I think the best way to introduce, I think I'll play the video of Professor Sebastian for 5-10 minutes, and then we'll discuss.
That is associated with the particle and its momentum was suggested by de-Broglie. We will discuss the de-Broglie relationship later, hopefully. But let me just remind you, because you would already be familiar at least a little bit with this. Let me remind you what the de-Broglie relationship is. According to him, imagine that you have a particle that is moving with a momentum which we denote as p. So here is my particle. It is moving with a momentum which I shall denote by the symbol p. And according to him, you say this particle, because of its dual nature, it has a wave nature, and there should be a wavelength associated with the particle. And so if I draw the wave would be something like this. And when I say the wavelength, what is the wavelength? The wavelength is this distance. It's the wavelength of the particle, and de-Broglie suggested that the two are related. Wavelength they will denote by the symbol lambda, and he suggested that lambda is given by the relationship is equal to h by t.
See, this is fantastic. See, lambda is given by h by p. What is h? Can you write it down? Shivalika, what is h? Planck constant.
So it is Planck's
Yes. Okay.
constant.
So it is h, you know, Planck's constant. What is the unit of h? Can anyone tell me?
Joule second.
Joule second.
Okay, joule second. So what is essentially, what is the dimension of h? I think that is the right question to ask. What is the dimension?
ml2 t minus 1.
What?
ml2 t minus 1.
ml2 t minus 1. Now, if you say joule second, it is essentially energy times time, isn't it?
Yeah.
Energy times time. What is the dimension of p? Momentum, linear momentum.
AML t to the power minus 1.
Okay, can you now tell me what is the dimension of h over p? What is the dimension of H over P?
L.
L.
Okay. Just check, is it? So I hope that. So if I write it here, so this, can you see the writing? Okay. So it says lambda equals to H divided by P. Okay. And this is called de-Broglie's hypothesis, isn't it? And this is called relation or hypothesis. Why it is called hypothesis? Any idea? Why it is called hypothesis?
So I think it was
Not
not
experimentally
that
proved.
time, experimentally.
What?
Not experimentally proved or something.
No, not really like that. I would say that you cannot derive it from any first principle. It is just like it came from nowhere. And if you assume that H divided by P, H divided by P is given by lambda, then you can build a subject like quantum mechanics, and the subject can explain many actually experiments which you perform with electrons, atoms, molecules. So how these electrons, atom, molecules, these subatomic particles, they behave, you can explain only using quantum mechanics. And you cannot build quantum mechanics without the hypothesis of de-Broglie, isn't it? So this is came from nowhere. Maybe Rahul, you want to add something to this?
No, this is pretty fine. This is pretty fine. Yeah.
Yeah,
So
actually, this is fantastic. Just try to get this. Because lambda
Just-
is given by H by P. It would not come to our mind, no? A common man's mind.
yeah. It's not derived from the first principle.
Yes, and what you can see that, okay, you know the dimension they match, but I can match dimension by taking many things. No? I can put something divided by something and make it length. But you see, you put H divided by P. Now here you see very carefully, P comes from classical mechanics. This linear momentum, isn't it? In a way. And not only that, in this case, if I draw a wave, so this is a wave. Okay, and then you know this distance is called the wavelength, lambda. Okay. And if you give me a wave with wavelength lambda, then I know what is the momentum of that wave, isn't it? Are you fine? Because if I give you a wave with a fixed value of lambda, then the momentum of that wave is fixed. Are you convinced? So can anyone tell me what will be the momentum for a wave with wavelength lambda? From wave mechanics, from wave physics, can anyone tell me? I'm waiting. Now, Ligesh, tell me. You are TA, no? You should tell me. Asha?
Planck's constant divided by wavelength of light.
Planck's constant wavelength of light. That is your de Broglie's thing. No, without the hypothesis. Just go back to your classical physics. And tell me what is the momentum associated with the uh, wave of say wavelength lambda.
Is it related to the E is equal to mc square?
No, you don't make things. That is relativistic. That is different. You're going to the relativity. No, I'm not talking about relativity. Just simple word. So what is the wave momentum? That is my question. Can anyone tell me? Now you say P is equal to mv. That is, but what is V then?
Sir, mass into wavelength by time.
Mass into wavelength by time. What is the mass of a wave? I don't know.
Oh yeah, sorry. Sir. In class.
Tell me.
So by equating p square by 2m equals to h nu.
Again, you are assuming quantum, no?
Sir, the k vector.
Hmm?
Can we think that particle, free particle, and the derivation for that we found P is equal to KH,
KH.
KH cut.
KH card. You're almost there, but again, you're going to quantum mechanics. I'm telling you from classical mechanics.
But sir, okay.
Can anyone tell me this question? I will not give you the answer. I'm just asking you this. You should know. Cannot bring mass, no? Here, we are talking about wave.
Sir, iota h का d by dx.
What? What?
Sir, iota h का d over dx for a particular wave.
So the question is very simple. What is the momentum of a wave with wavelength lambda? H by lambda. Yes, if you go to de-Broglie, this is H by lambda. But somebody said KH cars. Who said that? KH car. What is K?
K is the if we follow to the that derivative equation from there, K E minus B by 2m under root.
Somebody said KH car.
Yeah, myself I have said that, sir, and K is that E minus B upon under root E minus B upon 2m.
Don't make things complicated. K.
Sir, k is the wave.
Can we equate half mv
What is
square?
K? Rahul, what is K?
The k is 2 pi by lambda.
Yes, but what is this called?
Sir, wave vector.
Wave vector.
Yeah. And what is the relation of K with lambda?
K equals to 2 pi by lambda.
So what I have here is K H cross. H cross is what?
H upon 2 pi.
With H upon 2 pi. Okay. And this gives you H by lambda, which is your momentum, isn't it? So what I am saying that this is, if I assume, okay, you have a wave of wavelength lambda, then its momentum is fixed. It is given by this expression, de-Broglie. Rahul, you want to add something?
No, it's okay. It's okay. I can
There is a
hear the.
correspondence between lambda and p.
Oh.
Okay. Lambda and p. And how do you write a wave? You remember how do you write a wave? What is the equation? How do you write a say standing wave, for example? You know standing wave.
E equals to E naught cos omega t.
Okay, so you're saying something like cosine omega t.
Yes, sir.
This is your wave. And what should I write on your left? You're saying A naught. And this one I should write what? Can I call it psi? Something like that. Okay, is it a standing wave or something else?
No, sir, it's not a standing wave.
What is this then?
It is just a, a particle that is oscillating with time. It's not a standing wave. There should be a cos kx part to be a standing wave.
Yes. So what is that standing wave? Tell me. Roughly, tell me.
Yeah, so it will be A naught cos omega t cos kx.
And if I write this is fine. I don't want to write the time part. There is no time dependence.
Yeah,
it does not change with time. This is okay.
Yes, sir.
It's okay. It's okay.
And now you know what is this K?
2 by lambda.
Yes.
This is 2 by lambda.
2 pi by lambda. So basically, what I can write here, I can write it here something like A naught cos twice pi by lambda into x. I assume in one dimension. Okay, in x dimension. This is fine. So if I give you this picture, the one I drawn here with black pencil, this picture, the equation for this picture is this. This is not changing with time, isn't it? Okay, is this clear? This could be like cosine twice pi lambda into x. Is this clear? Okay. Others? Devojit? Choyon, you're from physics, tell me.
Yes, sir. No, it's not. Sir, what's the question?
So you're not even listening. I'm asking, the question is this picture, and the equation is something like cosine twice pi lambda into x. Is this okay?
Yeah.
Yeah, so it could be sine also, depending on, okay.
Yeah, depending on the origin. Yeah.
Essentially, what you have is cosine or sine with a fixed lambda.
Yes, sir. Yeah.
Okay, is this clear?
So what is this wave vector? I'm just trying to understand. What is this wave vector?
Wave vector is your tool. Okay, because it comes with because it also has a direction which I did not show you here.
Okay.
Because you should multiply this with some unit vector, which will give you direction. Because here, assuming you're making the things little easier, because momentum is also a vector, isn't it? It comes with a direction.
Yes.
I'm just making it clearer.
Okay.
To be speaking. So I'm just writing only the magnitude here. Okay. So it is essentially it is cos of or sine of something like twice pi by lambda into x in one dimension. Is it clear? So basically, if I give you the value of lambda and you know how to relate this lambda with momentum by de-Broglie hypothesis, I know the momentum of that wave. Is this clear? So the whole point is, with a fixed lambda, I have a fixed momentum. I repeat, I give you a wave with fixed lambda, fixed wavelength. I tell you, okay, this is the wavelength. Okay, say 100 nanometer or something like that, then the momentum of that wave is fixed. Is this clear?
Yes,
So,
Rashid, I think it's I think it can be added that the most general solution is e to the power ikx.
yeah, we'll add that. We'll add. But what I'm
Okay, we'll
saying,
come to that one, right?
yeah. So I'm saying that it is just a given value of lambda means momentum is precise. I know the momentum. For example, if I have lambda 1, then the momentum is say p1, then I give another wave, lambda 2, then the momentum is p2. Okay, only when you have a wave like this, which has a well-defined lambda. Is this clear? Any queries? Tell me. Is this clear? It's very important that you clarify, get these things. So the whole thing is okay. I give you a value of lambda, and then I know the momentum of that wave. Okay. Now, if I draw another wave, okay, this is a very bad drawing, but somehow you have to bear with this. This is another wave. And what is the wavelength of this wave? Can anyone tell me?
So it has no precise wavelength.
So Choyan says there is no well-defined wavelength for this wave. Because I don't know whether this is whether this is your wavelength or this is your wavelength or this is your wavelength. You know, I don't know. Is this clear? Any other thought? Vijaya, are you there? Vijaya Pathak, are you there?
Yes, sir.
Yeah. So anything you want to comment that this wave does not have a well-defined wavelength lambda? Are you convinced? Tell me what is your.
So I'm not sure.
You're not sure, but what Choyan says is correct.
Yes.
It does not have a well-defined wavelength because you cannot define. Where to define whether between this point and this point or this point and this point, you don't know.
Yes, sir. Exactly.
So what will be the momentum in this case for this wave?
We cannot find precisely the momentum.
So the question is, what is lambda? And then next question would be, what is P for this wave, isn't it? And this is not an easy question to answer. Or maybe very easy to answer. You say, okay, lambda is not well defined. There is no precise value of lambda for this wave, which basically means if I go back to de-Broglie's hypothesis, it tells you what? What does it tell you? So
We
Harsha,
can find momentum and wavelength.
Anyone wants to comment? Debojit, what does it tell? I'll take now names and ask people. Sorry. Yeah. So Prabal Gautam, tell me, are you convinced what I'm saying? See, this essentially tells you that since the lambda is not well defined, does not have a precise value, momentum is also kind of not well defined. I cannot say what momentum the wave has, isn't it? It essentially tells you that for this picture, the wave shown in this picture, it does not have a well-defined momentum. So we do not know with certainty what is the momentum of this wave. Is this okay? And many of you can guess in which direction I am going.
Sir, expectation value.
No?
Like,
No.
are we gonna?
We'll do
Heisenberg.
all these things.
Heisenberg
Localization of wave.
Heisenberg uncertainty.
Okay. If I give you a wave like this, you cannot tell me what is the momentum. I do not know the momentum of this wave. Certainly you do not know. So we are going towards Heisenberg. Yeah, somebody say yes, it is. So we will discuss. So maybe I can play the video of Professor Sebastian for some time and we'll come back.
Now, it's very interesting that de-Broglie actually belonged to the royal family. He was a prince, and originally he had wanted to study history. He was a student of history, but then he found history not very interesting, and he switched over to physics. And this was his PhD thesis. The suggestion was his PhD thesis, and the people did not believe in these suggestions, and the thesis was likely to be rejected. And if it was not for Einstein, it might have been rejected. And Einstein said that maybe there is some truth in the suggestion, and therefore the thesis was eventually accepted. But then at the time of the viva voce of the viva voce examination, the examiners actually asked him, this is all theoretically, can you suggest some experiment which will verify this relationship that you are suggesting? And then he said, you know that in the case of X-rays have a wavelength which is comparable to the spacing between atoms in a crystal lattice, right? And therefore you can see X-ray diffraction because the wavelength is comparable to the spacing between the different atoms in a crystal lattice. So maybe what you can do is you can have electrons, you can make them in such a fashion that their wavelength will match the spacing between atoms in a crystal lattice, and then maybe it will be possible to see the phenomenon of electron diffraction. It was suggested by him, and it was experimentally observed within 2-3 years, and therefore the relationship was experimentally verified. So what I want to tell you is an important consequence of this. One important consequence of this is actually the so-called Heisenberg's uncertainty principle. So to demonstrate to you how the uncertainty principle comes around or comes about, to imagine that you have a particle. This is the particle that is moving with a momentum as I have indicated p, and the momentum, I know precisely what the momentum of the particle is. If I know the momentum precisely, then of course I will know the wavelength. If this relationship is valid, I will also know the wavelength precisely, and the wavelength will be given by this relationship. So I know precisely what the wavelength is. And so what will happen is that I will have a wave which looks like this, and its wavelength is very well defined. So it will be repeating again and again with the periodicity that is equal to lambda. It will go on repeating again and again and again. In principle, it will extend from -infinity to +infinity. On the other hand, if I had a wave which is probably something like this, suppose I had a wave which is of this form, then it is not possible to say precisely what the wavelength is. Because you see, this distance, would you say is the wavelength, or would you say that distance is the wavelength? So wavelength is ill-defined for such a wave. So in order to have a very well-defined wavelength, I should have a very long wave with it repeating periodically in this shape, sinusoidal in shape, so to say. It has to go on repeating. So therefore, if you say, okay, this is the kind of wave associated with this particle, which has a well-defined momentum, and then if you ask me suppose I do an experiment where I'm going to find where the particle is. Suppose this is the wave associated with the particle. I mean, this is eventually going to be associated with my wave function, this wave that I have. So we know that maybe what I can say is, okay, wherever the value of the wave is large, we'll probably find the particle there if I do an experiment. So therefore, I mean, if you look at this, you can say the way it is drawn, at this location it has a value, and at that location also it has the same value. Even here it has the same value. My drawing is not perfect, but you can imagine it's perfectly periodic. And so you see that there are different points where it has exactly the same value, and therefore you would say, okay, if I did an experiment, maybe the particle may be found somewhere in this locality, or maybe somewhere there, or maybe somewhere there, or maybe somewhere there, and so on. Therefore, you realize that if I did an experiment, the particle can be found in principle anywhere between minus infinity and plus infinity, because my wave extends over such a region. And therefore, what has happened is that externally, if I try to determine the position of the particle, I would find that my answers each time is going to be very, very, very different. Sometimes I may find it here, some other times I may find it there, some other times I may find it elsewhere. So I will have a huge uncertainty in the externally observed values of position. That means if I denote the position by the symbol x, there is a large uncertainty in the value of x, huge uncertainty. So therefore, I will say that this is a situation where the uncertainty in the measured position of x is large. In fact, it would be infinity in principle if I had such a view. Now look at the situation why no momentum precisely, so therefore I have no uncertainty in momentum. Momentum is precisely known for this particle. So if I had delta p uncertainty in momentum equal to 0, then if I measure the position, the answers are going to be so different that I would have a huge uncertainty in the value of position. On the other hand, if suppose you say, no, I don't want this, I don't want the position to have such a large uncertainty, then what should I have? I should have maybe a wave which is of this shape. And this wave has the characteristic that it is 0. See, it is not 0 only in this location, this region, and outside the wave is. If I wanted to have such a wave, why do I want to have such a wave? If I had such a wave, when I measure the position of the particle, sometimes I will find it here, sometimes I will find it there, maybe sometimes here, and so on. But the uncertainty will not be very large. It will not definitely be not infinity. So here delta x will be finite. Correct? But then you ask, what is the wavelength of this? It means the answer is ill-defined. I mean, because you have to think of a wavelength for this. We will see how it may be done in the next few pictures. So this is my first wave that I talked about. The wave actually has a definite wavelength. It extends from minus infinity to plus infinity. Now suppose I want to construct a wave of this shape. How will I go about doing that? So it is made clear in the next few pictures. So you think of this red wave and you also think of this green wave. If you look at it carefully, you would realize that the wavelengths are slightly different. The wavelengths of the two waves are slightly different. They are not the same. And now suppose you added these two waves. What would be the result? If I am adding these two waves, the answer you can see what is going to happen. If you think of a point here, right at that location, the green wave has a displacement which is downwards. The red also has a displacement which is downwards. So if we add the two up, they will have a large displacement in the downward direction. Right? But if you thought of a point somewhere here, what will happen? The green wave has an upward displacement, while the red one has a downward displacement. The two will nullify each other. So if you added these two, what would be the result? It is shown in the blue curve that is shown here. I have drawn all the three waves. You see, this blue wave is actually the result of adding the red and the green. And you can see that by adding these two together, I have managed to have something which looks like this. Right? But if you actually added the two waves up, what will happen is that you will have this being repeated again and again and again. Okay, that's what happens. But the point is that by adding two waves of slightly different wavelength, I can actually make the wave function have a large value in some region and smaller values elsewhere. Right? But now suppose I am not going to add just two waves, I am going to add a large number of having slightly different wavelengths. Then what I can do is I can have a situation, this is actually mathematically possible to demonstrate, but we won't do that. You will have to believe me when I say I can have a wave which probably is of this form. Its value outside is 0, its value in that region also is 0, and the wave is localized only in this region. All the other regions, if I can cancel everything and have an answer 0 everywhere else, but only in a small region. But for that to happen, what I should have is I will have to add together several waves of slightly varying wavelengths. Right? And this is something that we can refer to as a wave packet.
Okay. So I hope everybody could follow. So the whole idea is that if I have a wave with definite lambda, then momentum is definite. So the uncertainty in momentum, if I have a wave like this, not very well drawn, but a definite lambda, well-defined lambda, then this will give me a well-defined momentum. Okay, but here the question is, what is the momentum? In this case, the uncertainty in momentum is 0. But here the uncertainty in momentum is very, very large. Can anyone comment on this? Any further comment? I hope people are online. Dheeraj Kumar Verma, are you online? Rahul, are you there? Hello?
Yes, sir.
The others are there. There is a lag maybe. Yes, so I am saying that the picture I draw I keep below. And please switch off, mute yourself, mute yourself. Please mute yourself, yes. So my lambda is well defined, so my momentum, so uncertainty in momentum is 0. But let us try to create something. For example, if I take this wave here, shown here, then, and this is your x position, no? X-axis. Now you can see that maybe the probability of finding this particle is here is high, here it is not so high. Again, it is here, it is high, something like that. So each time I try to measure the particle, I will find it either here or here or here. Okay, it is all over the place. All over the place, yes. Now let us try to create a wave which will be more localized in space so that every time I measure, I find the particle around that region. That's a very small region. So how to create a wave packet? This is called wave packet in position space. How to create this? So Choyan, I think you know about wave
Yes, sir.
packet.
Yes, sir.
Yes. So let us try to see. So the idea is as follows. So for example, I have a wave something like this, cos of kx. I call it omega. I could have called it kx. If I want to call it k, let us call kx. Okay, and yes, and so if I create the wave, it is like this. It's cosine function, isn't it? Can you see, all of you? I hope people can see. Just if you can see, say yes, I can see.
Yes, sir.
Yeah.
Yes,
Write it
sir.
down. Yeah, write it down. Don't need to unmute yourself, but you write it down because there is noise. So similarly, I can have another wave which has the same, which has a slightly different wavelength. Okay. I add a correction to that wavelength. Earlier the wavelength was some in arbitrary unit 1. It is 1.2 now. It would look something like this. Okay, and it would, if I plot them together, it would look something like this. And if I add them, what do you expect? What do you expect? If you add them, what do you expect? Any expectation?
We'll have a peak somewhere, and in otherwise cases, it will get interfered and it will cancel out.
Let us try to do it. Let us try to do it. This is exactly what is going to happen if I add these two waves. You understand? Essentially, I take two waves of two different wavelengths, lambda 1 and lambda 2. And if I add them, it would look something like this. Because, see here, if I, at this point, if I add this value plus this value, okay? So it will be something like here. Here, these two values will add. Here, this value, the red curve has value here, somewhere here, and the blue curve has value somewhere here, very low. So if you add these two, it will go down. So as a result, you can get to see something like this. So we're getting it slightly better, isn't it? So if I plot it, say, between, it's something like this. Can you see the picture? Just by adding two waves of two different wavelengths, lambda 1 and lambda 2. Can you see that? All of you? Very good. So now what do you expect if I add one more? If I add one more, what do you expect? If I add one more, let me do it. We are getting better. We are getting better, and we're creating something, yeah, which is more localized. So let us add even many more. If I add many more, let us see what happens. What do you get? This is exactly what happens when you add many more. You can see that there is a small region where it is very much localized and it is very, very small if I go away from that region. And this is certainly what is known as wave packet. This is time independent wave packet. There is no time here. Okay, so essentially it is what? It is essentially superposition of different waves, of different wavelengths. So mathematically, what is this? Mathematically, it is essentially sum over cosine of lambda ix, where lambda I varies from, say, some certain value to some certain value, isn't it? I take wave like waves with wavelength lambda 1, lambda 2, lambda 3, lambda 4 like this and add them. I take many of them and I get a wave packet which is localized in space. So if I have now, if this is the case, then what do you expect? So I have a wave packet. Let me draw it here. Which is something like, basically it is localized here. I have a very good picture. I can show it here. This is the wave packet. Can you see? This is very localized. So each time I measure, most likely that most of the time I'll find the particle there itself, isn't it? So I would say that if you have a wave like this, in this case, your uncertainty in X is very, very low. But what is happening with your momentum? Can anyone tell me what is happening with your momentum? Any answer? Now you can switch on your microphone. Very large uncertainty. Okay. Someone from BS. Many people have left. Someone from BS. Please. Momentum will become uncertain. Very high. Why momentum is uncertain? Tell me. Why momentum is uncertain? Tell me. De-Broglie hypothesis. So we have to relate the momentum to lambda. Okay. Now superposition of waves. So essentially what I am doing, I am taking many waves and I'm making superposition of these many waves. Each of these waves comes with a lambda. So lambda 1, lambda 2, lambda 3 like this. So each with a definite momentum P1, P2, P3. But when I superimpose, when I take a linear combination of these waves, my knowledge about momentum is lost because I do not have a definite momentum. So the uncertainty in momentum will be very, very large. And this is essentially what is known as Heisenberg's uncertainty principle. I think everybody knows about it, isn't it? Everybody knows about it.
Hello, sir. This is Ramanand. Can I ask something?
Yes, please.
Yeah, during superposition, we found only amplitudes are going to vary. How we clear out that wavelength is also going to undefinite, going to undefined.
Very simple, because every wave, now I cannot tell. So if you give a picture, this picture, tell me what is the wavelength of this picture. Whether this is the wavelength between these 2 points or between this point and this point or this point.
No, sir. It's variable. Yeah. Okay.
Yes. So only when I have a wave like this, the red one or the blue one, I have a well-defined wavelength and I have a well-defined momentum. And the uncertainty in momentum is 0. But I can find the particle here with equal probability, also here with equal probability, where with equal probability. I don't know where the particle is. So uncertainty in position is maximum. And then there is a relation which is given by Heisenberg, which says that if I multiply the uncertainty in position with uncertainty in momentum, say in x, it is delta x times delta px, right? Momentum of in that particular direction, and that is actually greater than equal to h by 2 pi or h by 4 pi. Now
4 pi.
4 pi, yes. Okay, so it is essentially in the order of h cross. H cross is your Dirac h, which is h by 2 pi. So it is h cross by 2. Okay, then this is known as Heisenberg uncertainty principle. What it says that, okay, delta x, delta p, they are always uncertain. Even if you create a wave packet like this, in principle, if you create a wave packet where the packet is picked at x equal to say something, x equal to x0 or x equal to 0, then the uncertainty in position is 0, but uncertainty in momentum is infinity. But it cannot violate that relation. Delta x times delta px is greater than equal to h cross by 2, which is a very small number. So I cannot go below that number. Okay, that h cross by 2, I cannot go below that number. And this is again a restriction. And this is also inbuilt in quantum mechanics. You cannot violate this uncertainty relation of Heisenberg. Okay, so I'm going to play the video for next few minutes, and I think we'll conclude from there today.
The mathematics of this I hope to discuss maybe after like 10-20 lectures. So that will complete, but this is the idea. So then, this is actually such a wave is a superposition of waves of different wavelengths. Now, why did I do it? Because I wanted to have uncertainty in position small. Uncertainty in position is now of the order of this distance. It's of the order of this distance, and this I shall denote as L. Okay. So this is a situation where delta x is of the order of L. And for such a situation, what has happened? The momentum earlier in this case, the momentum was well defined. There was no uncertainty in momentum. But to have this, I had to superpose waves of varying wavelength, and so momentum has become uncertain. Not the wavelength, which was saying momentum, I should say the wavelength has become uncertain. If the wavelength has become uncertain, naturally, if lambda is uncertain, then momentum is uncertain. So if you want to make this wave packet narrower, you can do that. But then you will have superposed waves of even widely varying wavelengths. Therefore, the moment you try to reduce the uncertainty in position, what happens? Uncertainty in momentum starts increasing. So there is an inverse relationship between uncertainty in position and uncertainty in momentum. This was mathematically analyzed by Heisenberg, and he came up with this relationship. He said that he could show, I mean, this is something that I hope to do later in the course, but here I am just giving you an overview. He could show that delta x into delta p must be greater than or equal to h divided by 4 pi. Okay, this is one of the consequences of this wave particle duality. And
yeah, so we'll discuss it from next class. Somebody like Krishnendu there. Krishnendu, are you there? Somebody ask a question. Krishnendu, are you there?
Yes, sir.
You're a MSc student?
No, sir. BSc. Yes, sir. MSc first year student.
First year. Okay. So he is asking that for a particle, it is expected to get only one wave, matter wave. So why we are taking more than one waves and superimposing them? Now the point is, you are thinking that you are superimposing them. Depending on the problem you study, depending on how we create the particle, it will have a wave associated with that particle. Okay. So I can create a particle which is localized in a small region. It cannot go out. So it will have a wave which is peaked around that region. It is zero everywhere else. So don't think that you are superimposing waves. We are doing it here mathematically, but depending on the problem, you see there's something called Schrodinger equation which you know. Depending on the boundary conditions, you create. Depending on the boundary condition, you get the solution, isn't it? And that solution will tell you what is the wave function for that particle. If I have a wave function for the particle which is shown like this, shown here, then the uncertainty in position is very, very small, and uncertainty in momentum is very, very high. Okay, we'll talk about in the next class. Okay, Krishnendu.
Okay, sir. Okay.
Yeah, so we can talk. I think we need few more classes to answer all these questions. For example, we're going to talk about something like particle in a box and see what happens there. We'll talk about eigenvalue, eigenfunction, then expectation value, all other things. So today I will just wrap up here. I'll conclude here. Okay, and I'll send you this recorded video as I did in the last, as I did in last week.
Sir?
Yes.
Sir, I have a question.
Yes.
So when we draw the wave function for the, wavelength.
Yes.
So considering it as an electron. So when we concluded that if the uncertainty in momentum is less, then uncertainty in position will be more.
Yes, well, it depends on if you draw this in x axis.
Yes, sir, and vice versa. So can we relate it with the conclusion that if uncertainty in position is more, then it will behave as a wave particle?
No, not like that. What I'm saying that every particle has wave nature as well as particle nature. Everything in this universe.
So can't we differentiate it on the basis of this conclusion that it will behave?
We can't and we should not actually. We should not. What do you gain by differentiating this? You should not. You say that okay, all these things in the universe they behave like a wave as well as behave like a particle. And when you build this subject of quantum mechanics, you will see that how it is done. Okay? You have this uncertainty in position and in momentum, but there's a bound. It cannot go below h by 4 pi. It has to be equal to or greater than h by 4 pi. Whatever you do, whatever experiment you do, you cannot go below this. You cannot violate this principle, Heisenberg's uncertainty principle. So you see that actually. What you are saying that if it is localized more like a particle, it is not like this. It is still it has a wave because you are explaining things based on a wave function, which has a wave nature, isn't it? So we'll conclude this session today. Yes.
Sir, I have a question.
Yes.
Sir, when we are considering a big particle, the big particle is made up of several atoms as well as electrons. So, sir, do we actually relate a wave with respect to that matter or with respect to every electrons and every atoms, and then superposition of all the waves?
Don't make things complicated. Now assume that you are dealing with an electron. If you deal with a molecule, you have a wave function, total wave function of the molecule.
Okay, sir.
I'm talking about total wave function. Linear superposition, this is just a mathematical practice right now. Okay. This is mathematical practice. What I'm saying, you're not really superimposing many functions like this. What I'm saying that it is the reverse problem. If I give you a wavelength, sorry, not a wavelength. If I give you if I give you a picture like this, I said this is your wave function or whatever, your wave. Then you see it is localized here and the values are very small if I go away from that region. And this is, you can think that as if it is made of waves of different lambdas. So that uncertainty in momentum is very high and uncertainty in position is very low. So this is the given, this is given. And in principle, you should get it from by solving Schrodinger equation, which we discuss in the next class.
Okay, sir.
So I'll conclude.
Hello, sir.
Now, but maybe I'll take one more question because we can discuss then over WhatsApp. Yeah, tell me.
So will we be discussing this eigenvalue and eigenfunction things in future classes?
Yes, obviously. It is a course in quantum mechanics, isn't it?
Yes, sir. Actually, I had one doubt, but then okay, so we can talk about it in next
When you
class.
discuss, you can ask me that question.
Okay, sir. Okay, sir. Thank you.
Okay, I'll give you an example how, for example, how to create a wave. Like not example, I'll give you an example of a function which is an eigenfunction of position. So each time I measure, I find the particle in a particular position. Okay. So I think now I will stop recording and